was to show that there are exactly n factorial permutations on a set of n elements. Okay. So proof that by induction. So I don't know where you want to start the induction, so you can start, okay, n equals 1 or n equals 0. Well, no, you don't. You can't start. If I do it as a group, you have to start with 1. So, okay, so how many permutations are there of a one element set? Well, there's only one. Which is the identity permutation, yeah, so that's okay. So 1 is 1 factorial, that's good. Now the induction step. Okay, so we assume that there are n factorial permutations of an n element set, and we want to look at n plus 1. And now there were muddled things saying like, okay, so what are we looking at? We're looking at all the permutations, so that's all bijections. I go from set 1 to n to the same set 1 to n. Okay, so sorry, n plus 1. I don't have the eraser. So the proof is not bad because I've made this error. The proof is bad because it's incomplete. Okay, so so what are they? So okay, so correctly you do. So there are some permutations where fn plus 1 is n plus 1. Okay. So when you look at all the n plus 1 to n plus 1 bijections such that fn plus 1 is n plus 1. So the size of this set, all the bijections between 1 to n plus 1 to 1 to n plus 1, such that the last element is mapped to itself. Okay, this is n factorial by the induction hypothesis. Because yeah, so that you've got you're looking at what they do on the first n elements and what they do, and that's a permutation of 1 to n, and then you add something to it. So okay, so I accept this, and this is n factorial. Now, I think to me there's a too big jump when you say that if some others f n plus 1 is not n plus 1, and then there's nothing in there, and some magic happens, and you write there are n times n factorial such permutations. Okay, that's true, but how do you know that? Well, you don't, because the induction hypothesis tells you nothing about how many bijections you have between the set 1, 2, 3, 4, 5, 6, 7 all the way to n, and the set 2, 3 all the way to n plus 1, for example. Okay, so you kind of think that it's the same n factorial, But the induction hypothesis doesn't tell you. The induction hypothesis only tells you that when you have 1 to n, and the number of bijections on that set is n factorial. But it doesn't say anything about when you have two different sets with n elements each. Okay, so but this the induction hypothesis is too weak for this. Okay, you see there's this difference because the induction hypothesis tells you if you have one set of n elements, then there are factorial permutations on it. But what it doesn't tell you is that if you have two distinct sets of n elements each, that there are unfactorial bijections. That's what you need to prove that. Does that make sense? Not really. Is it too early? Okay, so
what if that change was built into the definition of that set? What if we are?
But it's not.
Yeah, but I'm saying, what if what if somebody started by saying Sn is the set of all permutations from a n element set to itself? Would that be too imprecise at the beginning?
Yeah, no, but that still doesn't help. It doesn't matter if it's 1 to n or any n element set. You still need something else for this, and namely you need that if you have two arbitrary n element sets, and there are n factorial bijections between them. Okay, so it doesn't matter what the elements are called. So maybe I wasn't clear about this, but what you're assuming is that if you have one n element set, that the number of bijections from that set to itself is n factorial. Okay, what you actually need is when you have two n element sets, then the number of bijections from one to the other is n factorial. Because here, when fn plus 1 is not n plus 1, then you'll be mapping the first n element to some other n elements. Namely, those that remain once you've picked your n plus first element. Okay, and that is so. Okay, so I'm being maybe too rigorous, but I want to be too rigorous because it's a very simple statement. So we should really just be using fundamental things and be very precise about the proof rather than using it's the same. Well, I know it's the same, but then I also know that there are n-factorial permutations. So you just say, I know, and not prove it. So when you're asking me to prove something simple, then you shouldn't be using non-trivial jumps. So, a better proof. Is that I actually want to prove, so what we're proving by induction that if x and y are any sets with of the right size, so x and y is n, then there are exactly n factorial bijections from x to y. Okay. And then when you put x equal y equal 1, 2, 3, 4, n, that will give you the number of permutations being n factorial as well. So this easily implies the statement that you want to prove. But this is a bit stronger because it doesn't just talk about one set and the number of permutations on that particular one set, but it tells you for any two n-element sets that the number of bijections is the right number. And that in the induction step, that will be a sufficiently strong hypothesis to make the induction step. Okay, so here you can start with n equals 0 if you want, because there's just one mapping from x to y, and that happens to be bijective if x and y are empty, or you can start with n equals 0, n equal 1 if you want, doesn't matter. So I'll start with n equals 0, x and y are empty, and there is exactly 1. Okay, which is the empty mapping. And 0 factorial is 1, so that everything is good. So the step. So we're assuming validity for n, not copying all the things. So we're assuming that this is good for n, and now we have two sets x and y. The size is n plus 1. So pick an element of x. Well, not fixed, but I'm fixing it now, so I'm not writing it properly. So fixing it now in set x. Okay, and now when you look at all the bijections so how do you denote the set of all bijections from x to y?
To the parallel y to parallels.
And that's all mapping.
Oh, by checking it up, yeah.
Anyway, so then, so B, x, y. So that's all bijections. From x to y. So this B now consists, it's a union. Of all elements y, and okay, now I'm being silly. Okay, so what you do is you look at all the bijections. You've got this one fixed element in x, and you look at all possible places where you can map that particular element, and each of them. So this gives you a partition of all the bijections depending on where this one fixed element. Think of the number 1, for example, or n plus 1, or whatever you have in x goes. Okay. So this is similar to, I mean, it's just a formal notation, but that's what everybody who submitted kind of did. So where does the n plus 1 map to? Okay, it can map to 1, it can map to 2, it can map to 3, it can map to n plus 1, and so this is the same thing. Just I'm going through all the elements of y, and this one fixed element, n plus 1, goes somewhere there. Now, so what is each of these sets, actually? So they're disjoint, it's a partition. And now when you look at all the mappings where x goes to y, there are, so when you look f in, so I should probably, I'll call this by. So when you look at f in Vy, so that's a mapping from x to y that maps x to y, little x to little y. You can have f dashed, which goes from x, remove x, to y, remove y, and it's a bijection. Okay, so for every bijection between x and y, which maps x to little y, you have another bijection f dash that goes from a smaller set where I've removed the x to a smaller set where I've removed the y, and is a bijection by, which is defined um, on any a to be what f does on a. And this is one-to-one correspondence as well. Bijection. I didn't want to say that. So this is a one-to-one correspondence between this set and the set of all bijections from an n-1 element, n-element set, because we started with n plus 1, to an n-element set. So, so by the induction hypothesis, there are n factorial such bijections. And therefore, By has size n factorial for each y in y. Okay, but how many Bys are there? Well, there's one for each element of y. So Bxy has the size of y times n factorial size, which is n plus 1 times n factorial, which is n plus 1 factorial, and that's the end of the proof. Okay, is that daunting? It's very formal mathematics.
It's a lot more careful to, it covers all aspects. I think we might say something about why there's exactly one mapping from the empty set to the empty set. I mean,
well,
if you ask yourself what a mapping is, at this kind of level, when you're doing very careful arguments about sets, mappings are themselves sets.
Well, that depends. Okay, well, one model does sets. Yeah. Okay. So there's a set theoretic explanation why there are exactly. Yeah. So that's what Gillian said. So yeah, keep going.
So the mappings are sets of ordered pairs. Each ordered pair is an argument and the corresponding value. So in one way of looking at it is, what a map is, it's the set of all ordered pairs, of all possible arguments and their corresponding values in the map. And so then what's a map from an empty set to an empty set? Well, it's just the empty set of no ordered pairs, because there's no arguments or values to map between. So the mapping is the empty set, and there is only one empty set. There's never a multiplicity of empty sets, because sets are determined by their elements. So there's only one thing that has no elements, and that's the empty set. So that's why you'd say there's one mapping from the empty set to the empty set. But do you have an alternative way?
Okay, then there's the kind of I'd say category theoretic explanation where, well, more mathematical explanation. Well, okay, so what does it mean for two maps to be the same? Okay, they go from the same domain to the same codomain, first condition. The second condition is whatever element of the domain you take, both maps give you the same image in the codomain. So, so say FG are both from the empty set to the empty set, while the domain in the codomain is the same. So that's the first condition. The second condition for whatever element of the empty set, what is the image? Well, so then need to show that for any element of the empty set, f on that element is equal to g of that element. Okay, but so this is always true. So if you write for any element of the empty set something, then that's somehow voidly true always. I don't know. You should know that from your first year logic. Is it you or is it Said?
Yeah.
I mean, this is because this is shorthand notation for any A. A is in the empty set implies A equals GA. And so this kind of notation is in fact just shorthand for that implication. And if you don't know that this is always true, then at least you probably know that an implication with a false premise is always true. And this is always false because whatever A you take, it can't be an element of the empty set. So this is always false for any A, therefore the implication is true.
It's like saying every dog in this room is a poodle.
Yeah.
It's true.
It's true, it's a number of dogs. But
and it's also true that every dog in this room is an Alsatian.
So yeah, so somehow this is true, but if you don't do it in this stupidly formal way, but then still, I mean, you've got two maps from the empty set to the empty set, and on whatever they act, they give the same result always, because they don't act from anything. So yeah, so this is the first explanation. So the second explanation is somehow, I think it's semantic. You think more about what it means for two maps to be the same. And the first one is a bit more syntactic. Where in set theory, you define a mapping to be a binary relation with at most one image. Exactly. Okay, I'll shut up. Okay, too much of it.
Okay then. So remember, for the coset chapter, I've asked you to look at and to submit questions 6, 11, and 19. 11 was lemma 6.3. We did one of the cases of that in the lecture. 19 is a little general argument proof that H and K be subgroups, prove that the intersection of two left cosets is a left coset of the intersection. Okay. Remember, you've already proved back in the first groups and subgroups chapter that the intersection of any two subgroups is a subgroup. Okay, so that makes sense. That you need to remember that for that question as well. And then 6 is, I think, is the hardest of well, maybe the one that requires a little bit of thought. And it's a very concrete example. So you're talking about the general linear group GL2R. It's a set of all 2x2 invertible matrices with real entities. And we're asking what's the cosets of SL2R. So SL2R is the special linear group consisting of all 2x2 matrices with determinant exactly 1. Okay, that forms a subgroup. The group operation here is multiplication of matrices, remember? So this is a subgroup of GL2R. Both groups are infinite, of course, but this question is to, well, describe, describe the left cosets of SL2R, GL2R, and what is the index? How many left cosets are there? Remember, the index is the number of left cosets. Could be finite, could be infinite. And maybe if it's infinite, maybe we can try and describe what kind of infinite it is. So countably infinite, or have you got some other more well-known infinite set that can index all the left cosets, if you like. Okay, but to discuss some questions, I thought we'd first look at question 5. Question 5 gives us a variety of examples of groups and subgroups within them, and it's just to list the left and right cosets. This is a very initial exercise you do just to familiarize yourself with the definition of cosets. And just make sure you're okay. So first of all, we'll look at Z24. So Z24, remember, is the group under addition of the congruence classes modulo 24. We can think of it as representing each congruence class with its smallest positive representative. So it's number 0 through 23 under addition modulo 24. So what's this object? This is inside here. This is the cyclic subgroup generated by 8. Okay? So it's the subgroup generated by 8 under the operation of addition. Okay? So this is all the multiples of 8 that there are. So you've got 0, 8 itself, 2 times 8 is 16. 3 times 8 is 24, so you're almost tempted to write down 24 there, except you realize you've already listed it. Okay, it's there, 0, it's already there. Okay, so there's just that three element subset, and it's also a subgroup. It's a subgroup under the operation of addition. Okay. So what are left cosets of this in Z24? So if we look at the definition, with objects like these are subsets of the form A plus. Okay, when you define cosets in the book, we write the little g beside the subgroup H, but of course in this specific example, the operation is addition, so we'll use the addition symbol. So you've got the little element here plus the subgroup, where A is an element from Z24. Okay. So initially we've got 24 possible descriptions of these things. Okay, so you've got the 24 choices for A, the 24 elements of A. But how many left cosets are there actually? That's what we'd like to figure out here. I mean, we know ahead of time how many to expect. So remember some of the basic things we proved on our way to proving Lagrange's theorem about coset, about all the different cosets of the subgroup. So we proved the collection of subsets partitioned the group, split the group up into different subsets. And crucially, each coset had the same number of elements. Yeah, because this construction, or this where you kind of translate the subgroup across into other elements by adding on a fixed element from the group or operating on it with a fixed element from the group. It's like a bijection actually. Left multiplication by a fixed element is a bijection. Okay. So each coset has the same number of elements. So how many? So each left coset of this must have 3 elements. So how many of them do we expect within Z24? Sorry? 8. Yeah. Because we've got a 24 element set. We're going to partition it into cells with 3 elements each. Okay. So we expect 8 left cosets. as the size of Z24 divided by the size of the subgroup is 8. Yeah, and this thing is known as Jan was whispering to you, the index of the subgroup, cyclic subgroup, generated by 8 in its parent group, Z24. So, okay, we can list those. It shouldn't be too hard to list those. I mean, the first one, which one would you list first? Sorry?
The one we've already left.
The one we've already got, yeah. 0 plus 0, 8, 16. Okay, which is just this. Or 0 plus 8. And then, well, you just start listing them in order. You'll be able to list 8 distinct ones, and then you'll notice that they'll start to cycle around. Okay, so of course you can have 1 plus 8, so shifting everything by 1, shifting everything by 2. You get the idea. Until we shift everything by 7. Okay, so we have these 8 different cosets, and there aren't any more defined. If we try shifting it, picking another representative, the next representative, we might choose 8. But of course, that would just give us back this. So if you shift all these by 8 modulo 24, you get 8, 16, 0. You get the same coset. Okay. So these are the 8. These are the 8 left cosets. Now, the question asks for left and right cosets. Do we need to go through all of this argument again to determine right cosets? Yeah. So the operation is commutative. So when you define a left coset, this is the subset consisting of all sums like this, A plus an element from here. But of course, this operation is commutative. So all of those individual sums are equal to there when you write them down in the other way. Okay. So the operation for Z24 is a abelian. So the right cosets are the same. A plus subgroup 8 is always going to be the subgroup 8 plus 8 for every A in Z24. Okay. So any questions about that or queries on that? Okay. So let's look at some of these other ones. So 3 in U8. U8, remember, is Judson's notation for the group of units, modulo 8 under multiplication. So last year in number theory, we described this as Z8 with a superscript multiplication sign. Okay, the multiplicative group of all the integers modulo 8. You'll remember, of course, that the elements of this is every congruence class that's co-prime to 8. Those are the only ones that have multiplicative inverses. Okay, so the ones that are co-prime to 8 are all the odd ones. Okay, 8 is a power of 2, so it's all the odd ones. So it's 1, 3, 5, 7. This is a smaller example. It's just a 4-element group. 1, 3, 5, 7. This is the cyclic subgroup generated by 3. What is this?
1, 3, 5,
1, 3, 5, 7. So remember, it's all powers of 3 in this group. So 3 to the 0 is 1. 3 to the 1 is 3. 3 squared is 9, which is, well, the Conrad's class of 1. Yeah. So you only generate 1 and 3. The powers of 3. Yeah. So it's just 2 elements. Okay. So how many left cosets do we expect? So we're going to be partitioning this 4-element group by the cosets of a 2-element subgroup. So we just expect two cosets. One of them has to be 3 itself. Yeah. And the other one would be, we'll just take any element not from that subgroup and multiply it by the thing. So we should take 5 by 3, which would consist of the other 2 elements, 5 and 7. Let's do a quick check. 5 by 1 is 5, of course. 5 by 3 is 15, which is convert to 7. Okay. Again, when in this special case where there's only 2 cosets, well, again, okay, the operation here is commutative. So again, left cosets will equal right cosets. But in any situation where the subgroup is half the size of the parent group, there can be only 2 left cosets and 2 right cosets. Okay, but because the subgroup itself is always a left and a right coset, representative of the identity. Yeah. That means the other in this half case, the other coset has to be the complement of the subgroup. So in that case, left and right cosets will always be the same as well. It's a special kind of case. Okay, let's jump around a bit. Let's go to something quite different, which is cosets of T in C star. Now, you might be familiar with this notation. C star is the group of the multiplicative group of non-zero complex numbers. Okay. So you get a group of complex numbers under multiplication as long as you exclude 0. 0 would have an inverse. Okay. So multiplicative group of complex numbers, identity 1, etc. T is the subgroup consisting of the set of every z from z star such that the modulus of z equals 1. The unit circle in the complex plane, every point on the unit circle. Okay, that's a multiplicative group. And B, if you take 2 z1, 2 complex numbers from T, and multiply them, see, because the modulus of a product is the product of the moduluses, that will again have modulus 1. Okay, so that will again be on the unit circle. Okay, so z1, z2 is again in T. I mean, this straight away, I mean, if you're talking about complex numbers and things like this, straight away you should think about it geometrically. So there's radius 1 circle in the complex plane. There's your subgroup T. What are the cosets of this subgroup? Okay. Cosets of T in C star are the subsets of the form ZT, where Z is some element from C star. What are these cosets? Sorry? T is the set of complex numbers with modulus 1. Unit circle. So that's a subgroup. Take any 2 complex points here, multiply them. Of course, complex multiplication is a very nice geometrical argument. you multiply two complex numbers together on here, each of them has their own angle. The product is just the point which has the sum of those two angles. Okay. So actually, multiplying complex numbers from the unit circle, that's really just the same as adding their angles, okay? Modulo 2 pi. So complex multiplication is a very nice geometrical interpretation of the complex plane. That's where you're multiplying by things with modulus 1. But when you bring other numbers into it, numbers obviously unit circle. What are these going to look like? So there are different subsets of the complex plane that are somehow related to this subgroup that we're starting off with. So just at a point, what might they look like?
Would be a like circle.
Yeah, okay, so that's an excellent. Sorry? Well, I've asked them to, they've got the submission problems too. There's no harm to talk to these. But that's an excellent, okay, so like, what might the other cosets look like? I mean, well, it would be perverse if they looked like anything other than circles, really. Okay. So which circles?
Can they do the same circle? No?
No,
I'm so
the
confused.
same circle.
Well,
Well,
one
see-
of them is the same circle. But,
Yeah, so
every element is in the
If I took an element from the, remember, if you take an element from the subgroup itself and look at the coset generated by that element, it's just going to generate the subgroup again. You know, it's going to be that initial coset. But if we take something off, so suppose you take the complex number 2. Okay, just think of the real number 2, or the complex number 2. What happens when you multiply all of these numbers by 2? Circle of radius 2. Yeah. Okay. So that's a coset. Yeah. So 2, e.g., 2t is the circle of radius 2. But you know, you think about complex multiplication. If you take any z and multiply it by a t, the modulus of a product is the product of the moduluses. So that's going to be equal to the modulus of z. So this is where t was one of the elements from the group. It's a bit strange to call a complex number t, but if you take, so these are the things that make up the cosets, these products, z times t, where t is an element of the subgroup. What's the modulus of this thing? Well, it is just the modulus of z. Okay. So every element within the coset generated by z has the modulus of z. Okay. So it's going to be a circle of radius z. Okay. So zt will be the circle of radius.
making a jump.
Well, so how do I know that I get all the points? Is that your answer?
Well, you said that everything in the concept will have modulus, same modulus, but you didn't say that everything with the same modulus
Yeah.
will also be in the concept.
Yeah.
Oh, that's true.
Yeah, that's true.
You didn't say that.
Yeah.
And it will be because anything in the anything with modulus 1 is in t. So multiplying with anything in t is just rotating the number. Complex number. Like the same angle as this has. That's what Phillips said, I think.
Well, in fact,
On my bit of exploring. Okay, so multiplying by this number, complex number, any number in any other complex number, it means rotating it by that angle. So anywhere in the plane, you multiply it by this, means you rotate that by all that angle, and you end up somewhere here. Does that make sense? That's how complex multiplication works.
rotation and scaling. So when you multiply by a complex number z, represented as r e to the I theta, in its polar form, it's what you're doing to the other number that you're multiplying is rotating it by the angle of z and scaling it by the modulus of z. Okay, so complex multiplication is that very geometric meaning. Okay, so we can see that here in this cosines. Okay, that brings us to the end of that. So we're continuing with is it the next chapter, chapter 7? I think we skipped a few chapters. We go to chapter 9 on isomorphism. So we'll continue those lectures on Monday. And so please do the submission problems for Monday. So you see, like in this example, we were, cosets of T within C star. So you really have to think in the context of this group. What's going on with the operation in this group? How do things look in this group? That's very much the approach you should take to question 6. Okay, it's a completely different context, multiplication of 2 by 2 matrices and the special linear group. But so you want to think, get your thinking hat on very much in that context, multiplication by 2 by 2 matrices. This is the subgroup determined by a determinant value. All the matrices of value determinant 1. So think of the operation of multiplication of matrices. Think of how the determinant interacts with that, and that should move you towards an understanding of the cosines. Okay.